Stuck doing nested BFS from every cell? O1 matrix is the perfect test of multi-source BFS thinking. It shows up often in Phong screens because a brute force approach explodes, while the optimal solution is beautifully simple. Start from all zeros at once and ripple outward. Let's crush it with basics so you can narrate it confidently. We're given an MXN grid of zeros and ones. For every cell, return the distance to the nearest zero using 4 directional moves. Distances are shortest path lengths in an unweighted grid. Brute force, running BFS from each one, is O, MN2. Instead, think backwards. The nearest zero to a 1 is discovered if we start BFS from all zeros simultaneously. That's multi-source BFS. Push all zero positions into the queue with distance 0. Mark ones as, or unvisited, then relax neighbors. Complexity, OMN time and OMN space. Alternative, 2 pass DP sweeping top left bottom right then reverse. High-level steps. Initialize a dist grid. Put every zero into a queue with distance 0. Set every one to inf. BFS. Pop a cell. Try 4 neighbors. If dist near NC, greater than dist RC, plus 1, update an in queue. When the queue drains, dist holds the nearest zero distance for every cell. Let's walk through this solution. The main goal here is simple. For every cell containing a 1, compute its shortest distance to any zero in the matrix. If we try BFS from each one separately, the runtime explodes. If we use multi-source BFS, starting from all zeros at once, the distances ripple outward efficiently. Approach, multi-source BFS time complexity. OMN begins the method that computes distances for the entire matrix. Gets matrix dimensions. Stores the final computed distances. Tracks which cells have already been processed in BFS. Queue for BFS expansion. Loops through all matrix cells. When a cell contains 0, it becomes a BFS starting point. Marks 0 cells with distance 0, enqueues them, and marks them visited. Direction vectors for moving up, down, left, and right. Begins BFS. Expand layer by layer. Takes the next cell to process. Explores all neighbors. Checks bounds and ensures neighbor hasn't been visited. Assigns neighbor distance as 1 step further than current. Pushes neighbor into BFS queue and marks it visited. Ends neighbor check. Ends BFS. Returns the final distance matrix. Ends method. And that's how the algorithm works. Efficient, simple, and elegant. Now let's verify that the solution behaves correctly on the given test case. This grid contains zeros everywhere except the center. This matters because the center one is surrounded by zeros, so its nearest zero is exactly 1 step away. Short reasoning. All zeros enter the BFS queue first with distance 0. When BFS expands, it reaches the center cell and assigns it distance 1. All other cells remain distance 0. The output matches the structure of the input except for the center. This matches the expected result because every zero is distance 0, and the center one is correctly distance 1. So our solution checks out. The result matches the expected behavior, and the algorithm handles this test case correctly. Let's walk through this solution. The main goal here is simple. For each cell, find the distance to the nearest zero. If we only look in one direction, we'll miss shorter paths coming from the other side. If we do 2 DP passes, top left bottom right, then bottom right top left, everything balances out. Approach, dynamic programming, 2 passes, time complexity, OMN starts the method that returns the distance matrix. Gets number of rows. Gets number of columns. Creates a matrix to store distances. Sets a large infinity value, bigger than any real shortest path. Loops over all rows. Loops over all columns. If the cell is 0, distance is 0, otherwise initialize as INF. First DP pass, top left to bottom right. Scan each cell in row major order. Relax distance using the cell above, top neighbor. Relax distance using the cell on the left. Second DP pass, bottom right to top left. Scan cells in reverse order. Relax distance using the cell below, bottom neighbor. Relax distance using the cell on the right. Returns the completed distance matrix, ends the method. And that's how the algorithm works. Efficient, simple, and elegant. Now let's verify how this DP solution behaves on the provided test case. This matrix has zeros on the top 2 rows except the middle one, and the bottom row is all ones. It matters because some ones are directly touching zeros, while others are 2 steps away, which tests our distance updates in both passes. Short reasoning of how the algorithm processes the input and what it checks for. First pass sets 0 cells to distance 0 and others to INF, then relaxes from top and left. Many ones get distance 1 from nearby zeros. Second pass comes from bottom and right, updating any cells that can reach a 0 faster from those directions. The bottom middle cell ends up distance 2, while its neighbors are distance 1, giving the final matrix 0, 0, 0, 0, 1, 0, 1, 2, 1. This output makes sense. Every cell shows the shortest path to a 0, edges directly next to zeros are 1, the center bottom is 2, and all zeros are 0. So our solution checks out, the result matches the expected behavior, and the algorithm handles this test case correctly. Let's have a quick recap. Breakdown recap. We need the distance of each cell to the nearest 0 in a grid using 4 directional moves. It's all about finding shortest paths in an unweighted matrix. Assess recap. Instead of BFS from every one, mn squared, use multi-source BFS, inq all zeros with distance 0 and expand outward. Everyone gets its nearest 0 naturally in OMN. Structure recap. Initialize a distance grid. Add all zeros to the queue with distance 0. BFS outward. If a neighbor's distance can improve, update and enqueue it. Implement recap. usedeck for fast queue ops. Ran the multi-source BFS once. Clean, efficient, error-free on LeetCode. Check recap. All test cases passed. Distances matched expected results. Think in reverse. Start from known points and spread out. That's the power of multi-source BFS.